For the second hour of week 3, we are going to focus on an important concept, or two important concepts, which is the data similarity and dissimilarity. We're going to talk about what is data similarity, what is data dissimilarity, how we use each one of them, or how we measure each one of them. Okay, and it's important to note that these measures proximity. So if we can replace this title to be measuring data proximity. Now, similarity, as the name suggests, is a numerical measure, which means a number that measures two data objects, and it measures them how alike they are, how similar they are. Okay, so it's a numerical data measuring how, or comparing how two data objects are alike. The value is higher if the objects are more alike, and the values are usually between 0 or 1. So it's actually it's a range between 0 or 1. If it's 1, it means that the two objects are similar. If it's 0, it means that they are not similar. This similarity is also a numerical measure of how different two data objects are. Okay, so it is the opposite of similarity. It's lower if the objects are more alike. Okay, so this similarity is lower if the objects are more alike. The minimum dissimilarity is 0, which means if two objects their dissimilarity is 0, it means that they are similar, and the upper limit is actually varies between depending on the objects. So similarity or dissimilarity, they are called proximity. Okay, because in many cases we are actually measuring the distance between two objects. Now, in order to measure data similarity or dissimilarity, we will be introducing the data matrix. And a data matrix is actually a two-dimensional matrix, okay, containing values, just like the following, okay? And we're going to explain these, how these are distributed in a minute with examples. We use the data matrix to create a dissimilarity matrix. And the dissimilarity matrix will also be the same data matrix. However, we will only have a triangular matrix, because here we are comparing the objects to themselves. So an object, this object or this value to this value is their dissimilarity will be 0, because they are the same. This value and this value will be 0. This value and this value will be 0. And this value and this value, their dissimilarity will be 0. Now, we do not display, or we do not compute the dissimilarity values here, because it's going to be exactly the same as the one here. So that's why we actually only display this triangular matrix. First, we're going to talk about proximity measure for nominal attributes, which is similarity or dissimilarity measures for nominal attributes. A nominal attribute, we agreed that it's an attribute that takes more than two states. So an example here, that it's colors, red, yellow, blue attribute. Now, the first method for calculating the proximity of a nominal attribute is using this formula, which we call it simple matching. So the dissimilarity between object I and object J is the using this formula, which is P minus M divided by P, okay, where P is the number of matches between I and J, M is the number the P is the number of attributes, and M is the number of matches between the attributes. So, or the number of variables. So P is the number of variables and M is the number of matches. Now, P represents the number of attributes, which means that how many attributes are we using to compare object I and object J. So if we have one attribute, then P will be 1. If we have two attributes, P will be 2, etc. Now, the M here represents the number of matches. How many attributes that are matching between I and J. So how many attributes that are the same between I and J. Okay, now using these values, we will be calculating the value of the dissimilarity between I and J. And we will see an example towards the end of this lecture explaining this part. The second method is actually by changing the nominal attributes to a set of binary attributes. We're not going to go through how this method is done, but this is an example, or this is another method of calculating the dissimilarity in nominal attributes. Now we move to the proximity measure of binary attributes. Now the nominal attribute is actually is a generalization of a binary attribute. A binary attribute takes two states, which is 0 or 1, yes or no, female or male, positive or negative. So this is a binary attribute. Now, for binary attributes, it's actually the proximity measure if the variable is symmetric or asymmetric. And if the binary variable is symmetric, we will be following or will be using this formula. And if the variable is asymmetric, we actually will be using this formula. Okay, now these two will measure the dissimilarity in here, dissimilarity in symmetric variable, which is binary, and here dissimilarity in asymmetric variable. Now the values of R and S, Q, R, S, T, which are presented here in a form of a matrix, just as we explained earlier. I will explain in a minute how do we calculate Q, R, S, T through an example. Once you have these values and once you know this formula, you are able to generate a dissimilarity matrix for depending on the type of variable, if it's symmetric or asymmetric. Now we also have a Jaccard coefficient, and we use it to calculate the similarity, not the dissimilarity, the similarity for asymmetric binary variable. And the Jaccard coefficient actually goes as using this formula, Q divided by Q plus R plus S. Now, this is an example to calculate in how to calculate the similarity between binary variables, but we're going to take one example. Now, notice that here each one of these are considered to be objects. So Jack is an object, Mary is an object, and Jim is an object. And if we want to calculate the similarity or the dissimilarity, or we want to measure the proximity, it's all the same meaning, we will be comparing each object using only one attribute, or if we have multiple symmetric attributes, we can compare them together. But you cannot compare symmetric and asymmetric together because each one of them has their own formula. Now in the example here, we have 3 objects, Jack, Mary, and Jim, and we have gender, which is a symmetric attribute, meaning that male and female have the same importance. They are not different. However, all the remaining attributes here are considered to be asymmetric attributes, which means that yes and no are actually have different weight, have different importance. So yes, in terms of fever is important, and no is not as important as yes. Okay, we also have cough as negative, positive. Also positive is more important than negative. Also the test results for test 1, test 2, test 3, their values in terms of negative and positive are important. So this means that fever, cough, test 1, test 2, test 3, and test 4 are all asymmetric values, while gender is a symmetric value or symmetric attribute. Now, in order to be able to compute the similarity, we have to have all of them in unified way, meaning that all of them will have the same encoding. And usually we use zeros and ones or plus and minus, but here I'm using 0 and 1. So the gender here, I've given 0 to M and 1 to F. So males get 0 and female get 1. If I do it the other way around, it's fine, okay, because it is a symmetric value. And here for Y, which is yes, and positive, we will give it 1, okay, because if you remember when we spoke about binary variables, we said we give 1 to the most important value. Yes will get 1, and also P will get 1, while N, which is no or negative as well, will all get 0. So I simply translated this table into this table using zeros and 1 encoding. Now we want to calculate this similarity between Jack, Mary, and Jim using the gender attribute only, okay? Because it is the only symmetric attribute. However, if we want to calculate the dissimilarity between the asymmetric attributes, we will be generating dissimilarity matrix for all of these attributes together. So I will explain how we will create it for the gender, and it applies the same way for the other asymmetric attributes. However, the formula that we will apply at the end is different based on the previous slide. Now, this is to continue with the example. If we want to calculate the values of Q, R, S, and T, we will be generating for each one of them a dissimilarity matrix. So this is the similarity matrix, this is the similarity matrix, this similarity matrix, and this similarity matrix. Now what we will do is that we will first calculate Q. Q is actually having the first attribute as 1 and the second attribute as 1. Okay, so now first of all we will be listing Jack, Mary, Jim, Jack, Mary, Jim, which is the 3 objects that we have, and we agreed that we will only do a triangular matrix. Now we will be looking at the cases where the first attribute is 1 and the second attribute is 1. In this case, Jack is the first attribute and Mary is the second attribute. Remember that Jack is 0 and Mary is 1. So is Jack 1 and Mary 1? Then there are how many times? Never. It didn't happen. Only 0. طيب. Is Jack 1 and Jim 1? Actually no, because both of them are 0. Is Mary 1 and Jim 1? Mary is 1, however Jim is not 1, so 0 times. Now we move on to R. In R we will have, or we will find occurrences where the first attribute is 0 and the second attribute is 1. Remember that the boys or the males are 0 and the female is 1. So is Jack 0 and Mary 1? Yes, we have one occurrence of that. Is Jack 0 and Jim 1? No. Is Mary 0 and Jim 1? No. Okay? Now we move to S. In S, we will have the first attribute as 1 and the second attribute as 0. Now, Jack is the first. Is it 1? No, because even with Mary, Mary is 1, so no. Jack 1 and Jim 0? No, because Jack is 0 and Jim is 0. Now, Mary is 1 and Jim is 0? Yes, so we have here 1. For T, we have to have both attributes to be 0. And remember, we are referencing the table from the previous slide. So Jack is 0 and Mary is 0? No. Jack is 0 and Mary is 1. Jack is 0 and Jim is 0? Yes. Jack is 0 and Jim is 0. Mary is 0 and Jim is 0? No. No, never. It didn't happen. Now, to calculate the dissimilarity between, we'll just give an examples between these objects. So we have this formula from the slide, the slide that we've seen in the beginning. So the similarity between I and J will be R plus S divided by Q plus R plus S plus T. And now we just apply them. So the similarity between Jack and Mary, it's R, which is here, 1 plus 0, which is S, 0, divided by Q, which is 0, okay, plus 1, which is R, plus 0, which is S, plus 0, which is T. So it's going to be 1 over 1, and the answer will be 1. And if you think about it, Jack is male and Mary is female, then the dissimilarity should be 1. Now, if we want to compare the similarity between Jack and Jim, okay, so it is R 0 plus S 0 divided by Q 0 plus R 0 plus S 0 plus T 1. So it's going to be 0 over 1, which is 0. And if you think about it, Jack is male and Jim is male, so the similarity between them is 0. They are actually similar. Now, for the same example, if you want to calculate the dissimilarity between asymmetric binary variables, you will have to generate the values of R, S, T, R, S, Q. You don't need T, but you need, because the formula only requires R, S, and Q. You will need to generate them, and you apply this formula, and then you will get these numbers instead as the dissimilarity matrix. Now, the Jacquard's coefficient for non-binary variables, in this way we actually we use the set relations. We actually divide between the intersection between two sets over the union of two sets. So in the example here, if we have two sets, we have A with 5 values, and we have B with also 5 values. The union between A and B will be the set of unique values between them, and the intersection will be the shared values between them. And if you see it, the union consists of 1, 2, 3, 4, 5, 6, 7 values, and the intersection consists of 3. So the Jaccard coefficient for the non-binary variables here is actually the intersection of 3 divided by the union, which is 7, is actually 0.429, and this is how we compute the Jaccard coefficient. Now, if we want to standardize, and this is a subject that we will be discussing in further details when we move to future chapters, is the standardization of numerical data. And the standardization of numerical data will want to compute the difference between the difference, yes, between the value, the numerical data, and the mean. How far a numerical data is from the mean. Now, in order to do that, we calculate. One of the ways to do that is using the z-score. The z-score actually uses the data itself along with the mean, which we call it here mu, and the standard deviation. So the formula is x minus which is the x, which is the value that we want to calculate its z-score, and the mu, which is the mean, divided by the standard deviation of the mean. The standard deviation of the group. Now, what happens is that we will be calculating, using the z-score, we will be calculating the distance between x and the population mean, and divided by the standard deviation. So it will be in the standard deviation units. Now, if we get a negative score, then this means that x is below the mean. If we get a positive score, then x is above the mean. Now, another way to do that is, instead of calculating z-score, is that we calculate the absolute deviation. And this is the formula for the absolute deviation. And in that case, instead of using the standard deviation, we'll be using the absolute deviation. And it is considered to be more robust, meaning more reliable compared to the standard z-score measure. So using the z measure or z-score, we will be using the standard deviation. But we can use, instead of the standard deviation, we can use the absolute deviation, and in this case we will have a standardized measure for z-score, and it should be more clearer than the standard deviation. Now, we continue with this similarity matrix, but in this time we're going to use it to calculate the distances between data points, and in this case we have numerical data. Now, if you notice that we have these are objects x1, x2, x3, and x4, and we have 2 attributes for each one of them, and each object is actually can be represented in terms of a point in the x and y axis. Now, to calculate the dissimilarity matrix, one way to do it is using the Euclidean distance measure. And the Euclidean distance measure is something that we all know, but you may not remember it in the calling it as Euclidean measure. Now, let's calculate the distance between x1 and x2. The Euclidean distance we will calculate 1 minus 3, which is attribute 1. So the value of 1 and the value of minus 3, because we are comparing x1 and x2. 1 minus 3, and we will to the power of 2, which means 1 minus 3, which is minus 2 to the power of 2 is 4. And 2 minus 5, which is minus 3 to the power of 2, which is 9. So 4 plus 9, and then we will take their square root, and it's going to be 3.61. So it is a measure that you studied probably in high school, Euclidean measure of distance, which states that we will take the attribute 1 of x1 minus attribute 1 of x2 to the power of 2 plus attribute 2 of x1 minus attribute 2 of x2 to the power of 2, and then we will take the square root of their addition. So this is the Euclidean distance. Now, the Euclidean distance is actually a special case of the Minkowski distance measure. And the Minkowski distance measure, instead of having the value of 2, because we're using to the power of 2, we will actually have the value of h. Okay, so in this case, the Minkowski, or sorry, the Euclidean is actually a special case of the Minkowski distance between two p-dimensional data objects. So it is a more general form of calculating distance. Now, these properties here is just something that you need to know, that if the dissimilarity between the two objects I and j is more than 0, and I and j are not equal, and we also have the dissimilarity between I and I is 0. In this case, this is called the positive definitiveness. Now, if this dissimilarity of I and j equal the dissimilarity of j and I, in this case we call this symmetry. If the dissimilarity of I and j is less than or equal the dissimilarity of I and k plus the dissimilarity of k and j, meaning that it will be less than the addition of two dissimilarities of a point between I and j. In this case, we call it triangle inequality. And any distance that satisfies all of these properties is actually considered or called a metric. Now, as I said, the Euclidean distance is actually a special case of Minkowski distance, where h is equal to. So the similarity between I and j is the square root between two values squared, and we add them together, and this is the Euclidean distance. And this is the case if it was 2. If it was 1, so we don't have a square root, and we don't, we simply add them together. In this case, we call it Manhattan. If h equals infinity, in this case, we call it the supermum. Okay, the supermum is actually, it's the maximum difference between any component of the vector. So it's the maximum distance that any component can have. Now, this is the dissimilarity matrix, applying the formulas on the same example that we just saw. This is using the Euclidean. We already saw these values, and this is using the Manhattan, and here using the supermum. These are some videos. Some of them, or most of them actually, are not working. I will just confirm the links with the course coordinator, and once I have them, I will be posting them on Blackboard. All right, thank you very much. This is the end of the second hour.